Um, if you had a conical water tank that's filled with water and it's drained, and you want to find like how much water is left after a certain time, well, they would give you some information. They would say the amount of water is it's being drained at, I don't know, 2 cubic inches per minute, and if the original height was this, how much is left in the tank after this long? Doesn't that sound like an exciting problem? That's the kind of problems that we can do now because we have derivatives. So I want to kind of show you the setup of this, and then we'll actually do a problem. We're just going to kind of talk about the setup of this. The hard part of this is they expect you to remember some geometric formulas that maybe you don't remember, like the volume of a cone. We're going to take the area of the base of the cone, which is a circle, right? And how would you find the area of a circle? Pi r squared. That's the area of the base. And then you multiply that by the height of the cone, just like a rectangular prism. You take the area of the base, which is length times width, and then you multiply by the height. The same thing here. You take the area of the base, and you multiply by the height. That's actually the formula for the volume of a cylinder. Because we have a cone here, we kind of cut part of that cylinder off, and the formula is 1/3 pi r squared h. I'm sure you all remember that from your geometry class, right? The good news is, I don't know if your book gives you the formula, but on a test, if it's something like this, I'm not going to not give you the formula because I don't want you to miss it just because you know the formula. And I believe even on the AP exam, unless it's like a circle or a rectangle, they give you the formula for it. So they don't expect you to know it. So sometimes I like to just see if you remember it. And then here's what we're going to do. We want to find the rate which the volume is changing. And anytime they use the word rate, that means they're talking about the derivative. So I'm going to take the derivative of my volume function with respect to time, which means you have to multiply by whatever the variable is over dt. So like the derivative of v, we would say, is dv over dt. So it's kind of like implicit, only instead of multiplying by dy over dx, we're going to multiply by whatever variable's there. So humor me for a minute. Do you agree I'm going to need to do the product rule to take the derivative of this? Because I have r squared times h, both of those are variables. This is just a constant, so I'm actually even just going to write that as pi thirds. The derivative of r squared, do you agree that that's 2r? But because we're doing this with respect to time, I'm going to multiply that by dr over dt. Because it's the radius dr with respect to time. And then the product rule says I'm just going to multiply that by h. Do you agree with me? Plus, I still have this constant in front, which would be pi thirds. Now I'm going to multiply that by r squared, and the derivative of h is just 1, yes? But with respect to time, I have to multiply by dh over dt. So this is the big thing with related rates. Whenever they talk about the volume is changing over time or the radius is increasing over time, anytime they talk about that, that means you're doing a related rate problem. And so I really just want us to maybe kind of be able to recognize when we need to do this. And then we don't have any numbers to plug in right now. I'm just going to kind of simplify this, and then I think, oh no, just kidding, I don't even have another problem for this. But the problem would give you something, like they would tell you what the radius starts at, they would tell you the radius is changing at a rate of blah-de-blah, that's what goes here. They would tell you that what the rate that the height is changing, and there'd only be one variable to solve for, and we're going to do an example of that, but I can't really do much here. I can take out a pi thirds. I really could take an r out also if you wanted. And I would be left with, what, 2h er over dt plus r times dh over dt. And I'm on your homework, they're not going to ever leave you, like you're not going to leave something like this because they're going to actually give you something to plug in. I just wanted to kind of show you how the process goes before we jump in to a problem. And so it's kind of important to think about that. Here, I'll even just write this down here. dV over dt is the rate at which the volume is changing, and the dr over dt is the rate that the radius is changing with respect to time, and the dh over dt is the rate that the height is changing. And so just like when you see the word tangent line, or when you see the word slope, or you see the word differentiate, or instantaneous rate of change, all of those mean derivative. If they talk about something changing with respect to time, that also means the derivative. And so it's kind of like a new little vocab word to add to our derivatives. And so this, I feel like the guidelines to this are pretty much like the other ones, except for usually you only have one equation now. And so the nice part is I printed these out for you. These are kind of just the guidelines to think about. Usually a good point of reference is don't plug in any numbers at the beginning. You want to take the derivative of your function to begin with. So that number one, identify all givens and quantities to be determined. Make a sketch if needed. Write an equation involving variables whose rates of change either are given or are to be determined, which means don't plug in what you know right away because you need to take the derivative. You need to find dr over dt, dh over dt. And then this is kind of a new thing. We're going to take the derivative with respect to time. So that's where all those rates of change go in. And then we'll substitute in what we know, and you should be able to solve that problem. Some are easier than others, and some are kind of just crazy. So let's see if we can get through, I don't know, at least two of these. The first one's not really a story problem at all, and so we'll just start with this so you can kind of see the setup of it, and then we'll see if we can do the example 2 so you can see what's happening, and then we probably won't get to the baseball diamond. So. To the baseball diamond? We should. No, it's too cold. When I taught geometry at my old school, and we learned how to find the area of any regular polygon. I don't know if you remember that formula, but like if you have a regular octagon or a regular pentagon, you can find the area of it by drawing in the apothem, and there's all this rule about it. But I gave my kids extra credit if they went out and really measured the area of a stop sign, and they had to take a picture of themselves, like standing at the stop sign, so that I would know they really did it. Only one kid did it, so it's fine. Probably kind of dangerous. And I didn't realize how high stop signs were until kids were trying to stand on a stool in a row to reach up and measure the stop sign because they're very high off the ground. Most of them. Okay, so this is not a story problem, but they are going to have us use related rates because we're going to find dy over dt with respect to time. So they give you the function. So the nice part is you don't have to write an equation using area or volume. And they also give you dx over dt, and they want us to find dy over dt. And so if this were a story problem, our first step would be to find our equation, but they give it to us. So my equation is y equals x cubed minus 4x. And this is the part I just want you to kind of think about. Normally, when we're doing a story problem, you want to plug in the numbers that you know right away. Like you would say, oh, I know x equals -3, I should just plug that in. But we want to get it in terms of those rates. We need to solve for dy over dt. We need to have dx over dt in our problem so that we can plug that in. So the first step after you get your equation is take the derivative of that function with respect to time. So instead of just writing y prime here, with respect to time, I can say dy over dt equals, and again, unless you're taking the derivative of time itself, you have to put that over dt there. So when I take the derivative of 3x, x cubed, I would get 3x squared dx over dt minus 4 dx over dt. You agree with me on that? Where I'm getting those values? And then plug in what you know and see if you can solve for what you're looking for. In this case, we're trying to find the rate of change for y. We're trying to find dy over dt. Sometimes you might need to do, like those optimization problems, you might need a secondary equation to do some sort of substitution. But we're good here. If I want to solve for this, I know what x is. I can plug that in for x. And I know what dx over dt is. I can plug that in for dx over dt. And your answer will be dy over dt. Does that make sense what I'm saying there? So x is negative 3, and dx over dt, or the rate of change of x, is negative 2 minus 4 times negative 2. And really, I probably should plug in next to negative 2 that it's negative 2 centimeters per second. My professor in my class informed me that I'm doing my math incorrectly when I don't carry my units the whole way through. She also wrote on my paper yesterday that I got back. I said you plug this into the equation, and she wrote you plug in appliances, you don't plug in equations. So apparently, you should never use the word plug when you're talking about math. So, thank you, professor. They will write you a really mean paragraph. What do we have here? 9 times 3 is 27 times negative 2 is negative 54. No? Yes? So dy over dt is negative 46. And since we're talking about the rate of change, it's how much is y changing over time. That's where the units come in. Dx over dt was negative 2 centimeters per second. And so this would also be negative 46 centimeters per second. Doesn't really make a whole lot of sense when there's not a problem to go with it, but the first part of your homework is like this. I just wanted to kind of show you how to do it. I think it's a homework, maybe you'll ask that. If it makes more sense, I think we need to put a story problem there. So let's try number 2, and we'll see where our time is. Anyone have a question on how I did that? All right, so this says the radius of a circle is increasing at a rate of 2 inches per minute. Find the rate of change of the area when r equals 6 inches and when r equals 24 inches. Which means it's two problems. But they're telling us that the radius is increasing at a certain rate, and they want to know, because the radius is increasing, how is the rate of the area, like how is it changing as the radius is increasing? So the first thing you have to do is figure out what equation you're using. And if we're trying to find the rate of change of the area, what equation am I going to use? The area of a circle, which is pi r squared. And sometimes I don't do a great job of writing out all my variables. But if I get stuck, I always do that first. And so I just want to kind of show you that if you wanted to write your variables out here, you could say r equals the radius, a equals the area, and then we're going to add in the rate part by doing the derivative. So if the rate of the radius is increasing at 2 inches per minute, then that would be the rate of the radius, which would be dr over dt. Right, so whenever you see that word rate, that means it goes with the derivative. And it's increasing, that would be 2 inches per minute. If the rate of the radius was decreasing, how do you think we would write that? Negative 2. So it's important. It doesn't say negative 2, but it says decreasing, so you know to put a negative number in there. And then we're trying to find the rate of change of the area, which would be the a over dt. That's what we're looking for. And so I don't do a great job of this all the time, but sometimes the problems are a lot more complicated than this, and so I just wanted to kind of show you that guidelines. This is what I mean by identify everything that you know and everything you need to know. And they do actually give us the radius, 6 and 24. We're going to do that twice. After you do that, you're just going to take the derivative, and the derivative of a is just 1, so we get dA over dt. equals I go if I write 2 pi r because you're writing the derivative. Is that it? Times dr over dt. So the rate at which the area is changing is equal to 2 times pi times the radius times the rate at which the radius is changing. So write your equation, take the derivative of it, and then the last step is just plug in what you know. And this is where you're going to do it 2 times because there's part A and part B. So for part A, that's when my radius equals 6 inches. And just to show you where these units are coming from, dA over dt is going to equal 2 times pi times the radius, which is 6 inches, times the rate at which the radius is increasing, which is 2 inches per minute. And that's 24 pi. Do you agree with that? Since this is a related rate problem, it's really important that you do put the proper units on there. So if you put the units in your problem, you should be able to see that inches times inches is square inches per minute. And so it is important that you put the units with that. AP free response, usually if there's a problem with units on it, 1 point for the answer, 1 point for the correct unit. So even if you got the numbers wrong, you would get a point if you put the correct units in the problem. So that's where if you put the units in, that you don't have to think about it. And you just do the same thing for 24. 24 inches times 2 inches per minute. And I just left pi because that's an exact answer. And I think this one is 96 pi square inches per minute. And it should make sense that the bigger the radius is, the faster that that area is increasing. Right? Does that make sense? So that's not the area of that circle, it's just the rate at which it's increasing when the radius is increasing. Does that make sense of what we're finding here? What time do we get out here? Too soon. 12? Let's see if we can at least look at this lovely baseball diamond. What is that? That's a baseball diamond, and that's a guy running. See, that's his head, and that's his feet, and he's running. Okay, so this one is a little bit harder, and I don't know if we're going to get this finished. But, what? It's just the basis, right? Like, it's just running from home first, second, that's square, right? Sorry, I should say a baseball infield. Is that what I should say? Don't you call it the baseball diamond, though? And if you include the outfield, is it really a diamond? Yeah? I don't know. I'm not good with baseball. 90 feet long sides. We should all agree with that. A player 30 feet from third base is running at a speed of 28 feet per second. It's pretty fast running, I do believe. At what rate is the player's distance, S, from home plate changing? So I put S in here. The player's distance from home base. That's what home base. That's what we're trying to find. So that's going to be what we're solving for eventually. I used X as the distance from the player to third base, which they actually give you. But again, you have to label the variable if you're going to take the derivative of this. So I wrote X equals 30 feet, because the player 30 feet from third base. But I need to write it as a variable because this would be the player's distance from third base, but we also have the rate that he's running, right? Like the rate of the distance. Does that make any sense at all? So I said the rate that is changing, right, as he's running, I said the rate would be 28 feet per second. Do you agree with that or don't agree with that? What else do we know? S is what we're trying to find. S is the distance from home plate. Actually, we're not trying to find S. What are we trying to find? We're trying to find the rate that's changing. Do you agree with that? So we're going to leave that blank right now. ds over dt is actually what our answer is going to be. Find the rate that the player's distance is changing. Could you tell me what S is in this problem? If right here he's 30 feet, do you agree this is 30? And we know this is 90? Could you tell me what his current distance is from home plate when he's right here? How could you do that? Pythagorean theorem? What? Square root of 9,000, yes. And I wrote that as 30 squared to 10. Because I wrote 30 squared plus 90 squared equals s squared. And you're right, it is the square root of 9,000. And I just wrote that as 910, and the square root of 900 is 30 square root of 10. And I think that maybe we'll just stop here and pick this up tomorrow. But I'm still going to go ahead and let you look at your homework tonight and see what you can figure out. We still have some stuff to figure that up here. So let's pause with this. I only have 5 problems for you. You might want to write that the surface area of a sphere, I think you need to know that for your homework, is 4 pi r squared. And I believe that that same problem, the volume of a sphere is 4/3 pi r cubed. And then the last problems, like 19 and 23, probably going to have to think about those a little bit. Maybe at least try to get the picture set up, and then as we finish that problem tomorrow, we can talk more about